hope you can hear as well. Can you maybe confirm? So you can just write in the chat. You can also use the chat in order to write questions to us. So yeah. So well, we're very sorry for our delay. There was also like we're down underground now, about 100 meters under the earth. So there are sometimes just some things that don't go quite as we expect on the top surface. Right. Let us introduce ourselves first. So maybe you want to start?
Okay. Yes. My name is Divya. So I am a postdoc here working at CERN. We are now at CERN. I'm working in the ATLAS Experiment as a postdoc with the Triumph Laboratory in Canada. I did my PhD working in ATLAS Experiment, also in dark matter models. So I'm working in Higgs models, well, in the Higgs production and in dark matter model system. And yeah, I'm very happy to be here doing this little visit in ATLAS.
Yes, and my name is Silvia. I'm also a postdoc. I'm also working for ATLAS. And yeah, so actually what is a postdoc? Maybe that's interesting for some of you. So this basically means we have done a PhD, and now after doing a PhD, so after being a doctor, basically we continue working at an institute. So I work for the University of Bern, and I'm actually based in Bern, and I'm sometimes at CERN. Right, so why, like what is so important or interesting about CERN? Well, CERN is the Centre Européen de la Recherche Nucléaire, so it's our, basically it's just like a center for nuclear research. Well, nuclear research might sound a bit odd because what we do here most of the time is actually particle physics. And so what we want to do now, we want to show you a bit of what it means to do particle physics research at CERN. So I think we should first introduce CERN a bit more and where we are. So maybe you want to start introducing.
Yeah, and before that, don't forget we have also the chat is being monitored. So any question you want to ask us, any comment, anything you want us to mention or to go and see further in the detector, don't forget to do it.
Yeah.
So I'm here monitoring that. So yeah, so here we are at the ATLAS experiment, which is one of the four main experiments of the Large Hadron Collider, the LHC. This LHC is a huge particle accelerator that is in the frontier of Switzerland and France. It has 27 meters, kilometers, so it's huge. And then in these different four experiments that are in this big ring of the LHC, we have ATLAS, CMS, LHB, and ALICE, and in those experiments, we collide protons. Yes? So what happens is that we inject protons, well, a bunch of protons in one side, in one direction of the LHC, and in the other direction of the LHC, and we make them super energetic, super fast, and then we try to collide them in those points, and then in these huge experiments, we try to see what happens after the collision.
There's just a comment about the noise. If you can move your microphones a little higher to your neck, that'd be great.
So let us know if this is better for you guys.
Yeah. So I hope you can hear me well.
I mean, they can hear you, but it's just a little noisy.
Well, yeah.
Okay.
Let's see if it works. Yeah, so let me continue also with what you were talking about with the injection in LHC. So what I think is important and interesting is that the accelerators we're using at CERN are actually, like some of them are very, very old. So CERN is now celebrating its 70th anniversary. So this means in 54 it was founded, and actually the first accelerators were built in the 50s. So what we do in order to have protons inside LHC for collision is that they go through an acceleration chain. So there are, it's like protons are coming actually from the hydrogen bottle. They then be accelerated in a linear accelerator, and then they start going through an accelerating chain of like several circular accelerators. Yes, so until they finally reach the LHC where they collide. So now, why do we actually want to collide particles? Well, what we want to understand is the basic building blocks of the universe, so the building blocks like of matter in a way. And so what we do when we collide protons is we have the collision of the constituents of the protons, and then many new particles come out. And now with ATLAS, which is kind of behind us, a gigantic, it's a monster basically, experiment. What we want to do is we want to take a photo of this proton collision. So basically what you can picture is that this whole thing is a gigantic camera. So it's a bit like the camera that we have in our phones. So there's like, yeah, active material where we can sense the particles when we have been given an electric signal, we will explain a bit more about this, and that's not what we read out. So in order to actually do with physics. Yeah. All right.
Something super cool to see from here is that the size of the cavern, no? Because this experiment is huge. It's 25 meters times 40 meters.
46. Yeah.
46, wow. 46. So it's huge. Even to go up to here, we need to take an elevator. We are actually in the 7th.
I think we're the 10th floor and the 11th
10th
on top.
floor.
Yes.
So it's really, really huge. And we don't worry, we will see more on the other floors where you can really see the picture of how awesome it is. And also something we can see here is this point.
Yes.
Yeah.
So I think we should show you the access shaft. So this, what you can see now, hopefully in the camera, is actually where ATLAS came through. So what I find interesting is that ATLAS is basically built like a ship in a bottle. So we have some parts coming down through this access shaft, and then they are being assembled to the ATLAS detector. I will point out later which parts came down as a whole, because they're actually really big. So as she was mentioning, the detector is 25 meters high. So as you see, we are above the detector, so like with respect to the cavern floor, we're more than 25 meters high. And the length of the cavern is also more than 46 meters, what is the length of the detector. Alright, so what I think is we should go down some of the stairs here, and then we can start introducing you to the specific parts of the detector.
Okay.
Maybe something we can see from here that maybe we cannot see from below is something super cool. That is a very brand new detector. There you can see the new small wheel. We will discuss maybe this later, but this is a very nice view of it. It has like these brownish petals, and yeah, I don't know if you can actually see it, but I think it's super nice view of it.
Yeah,
from
so
here.
exactly. So she was just saying it's new, so that's actually something that is very important, I would say, because this detector has been here for quite a while. We started with the LHC in 2008, I think. So the detector was ready at that point, and of course the detector is like needs to undergo some maintenance, maybe some small repairs. And what actually happens regularly is that also like whole parts are being exchanged. So the new small wheel is part of the immune system, which I will explain in a bit. And it was completely replaced, I think, 2.5 years ago. So it's kind of, in our terms, it's very new, and it's very, yeah, it's quite interesting and cool for us to see how really parts get completely replaced. All right, so maybe as we can actually see from here, we can kind of give a general introduction about. Is my microphone still open? I'm going to put it closer.
It's unclear whether or not the mics are picking up the sound, so
Okay.
we'll just stay near you.
Yeah, maybe I'll just hold it like this, and then we're going to see how it works. Okay, so let me introduce like a tiny bit the general idea of the detector. So we were talking about we have protons colliding in bunches. So what this means is that we have several protons at the same time, kind of in a cloud, and then they're colliding. So also the protons is not an elementary particle. So inside the protons are further particles, and this is actually what is colliding. So the constituents of the proton collide, and when these two bunches cross each other, there is also not just one interaction, but there can be like up to 40 or 50. So basically what happens inside this detector is that we have a bunch of particles colliding and producing new particles. So what we want to understand is where exactly did these particles like collide, so we want the exact position, and then we want to see the new particles where they came out. So we have inside a vertex detector that is telling us where is the interaction point. Then we have a tracking detector around where we can see the tracks, so kind of the distance, or not distance, like the way, the path that the particles traveled. Around that we have a calorimeter, and you should know the word calorie, right? So when we eat calories in order to have energy to do our everyday work. So if we put particles in a calorimeter, we measure their energy. And then around that, we have immune system. So now what is immune? Well, what particles do you know? So I think you all learned in school that there is like, we have atoms, right? So if we look inside an atom, we have the nucleus. If we look inside the nucleus, we find the protons and the neutrons. I talked about the protons before. They consist of quarks, so actual elementary particles. Neutrons kind of similar. And then around this are the electrons. So this is all particles we know. Electrons we also know from like electricity, so we have moving electrons, so this gives us electricity to do all the things we do. Well, now, what is a muon? Muon is basically the bigger brother of the electron. So it's like 200 times heavier. This also means that it's not really being stopped. So the biggest part of our detector is the muon system. So everything that you can see here, you see these like, the striped kind of, the striped thing there with these orange stripes. Everything inside there is the muon system. Also, these things that we see here, these are big wheels. You will see soon that this is a wheel. This is also part of the muon system. And what we mentioned before, the new small wheels, so inside where you see these, the striped things, is also part of the muon system. So basically, the biggest part of ATLAS is actually the muon system trying to measure, the muons. So why are muons interesting for us? Why is it exactly muons? We talked about physics before, so many of the interesting events do actually have muons. So for us, it's kind of important to be able to measure muons properly.
Trigger.
Yeah.
You want to go down?
Yes, let's go down. You know, we can also show them the layout of the ATLAS, so we can see better these detectors that we were talking about. Yeah. It's a bit of not usual, but we're going to manage. Is which?
It's mine, but we'll get it.
So our camera.
Yes, so maybe we can make a tiny stop here.
I lost my badge.
Okay, so we can just show you one thing. So it's important actually for us that for it to go down here, we need two things. So we need our dosimeter. So this is something where also our biometric information is basically saved. So they scan our iris to really confirm who it is. And then we also have our access card. So on the access card, we can actually open doors and everything. So
Yes. And also super important, the helmet and the shoes. The shoes are safety shoes, so there is a huge amount of security that is going on, training, because this is an experimental area. So there can be radiation, there can be gases, there can be a lot of things going on. So we need to be prepared and very well trained. So going down in ATLAS detector is not that easy as it seems. But okay, you want to show something about the
I wanted to show the muon system because from here we can go very close and we can go on several parts. So this is the part of the big wheel, and we have here one type of muon detector. So you can see it's tubes, and inside these tubes they actually gas filled, and then inside there is also a wire. So it's going all along the way. So basically what happens is when these muons go through, they ionize the gas, and then they kind of travel inside to the wire and leave an electrical signal. And then this electrical signal comes out with the cables. There are cables everywhere. You see them all the time. So we have our whole cavern is we have tons of cables, but we also have many pipes where we transport the gas to the tubes and everything. Yes.
Which is super interesting because this is done by a person. Like a person has to really do this and connect and put this for all of these 46 meters on.
Yes.
So imagine all this work and all this cable. I think that is always super amazing. You can see, for example, this amount of cables and gas pipes. Everything is handmade with a lot of love, which is super nice.
And so to talk a bit more about these pipes, so you see that they are in different angles. So here they're kind of angled like this, while here they don't have an angle quite as strong, and in the middle they're actually straight. So what we need now, we need always the cable to be, like the wire, to be exactly in the middle of the tube. So basically this means that the tubes are somewhat bent a tiny bit because due to gravitation and being them like hold on both edges, they do bend a tiny bit. I think this is super cool. I've never thought about this, but so they don't hold exactly the same. They all kind of bend a tiny bit. Yes. So there's really a lot of work in there. It's all custom made. We can't really use anything commercial. Right. Let's go further down to show you the detector layout, because then you can understand a bit better how it's all connected.
And also, don't forget the questions. I'm still waiting for your questions here in my phone.
What I wanted to mention also, so we talked already about the muons and how they are very important because they have very important signatures. So now I wanted to mention actually how many times, how does it work with the collisions? So what we actually have, we have very high collision rates. So the protons arrive here and have bunch crossings at 40 megahertz, so 40 million times per second. That is actually quite a lot. And as I mentioned before, we don't just have one interaction in one bunch crossing, but they can be up to 40. So we can basically say that we have something like more than 1 billion proton-proton interactions in one bunch crossing. And how do we deal with this? So this is a lot of data. So this is, well, do I have the number? I think it's also more than 1 million megabytes. So it's really a ton. So what we need to do is we need to kind of get the data down. So we have several trigger systems. And one of the trigger systems is actually like part of the muon system. And if you go through the score, you can see it. Because basically, I mean, so triggering for, when I say triggering for me, it means we need to find out the events that we're interested in and discard the events we know. An event is what we call when there is a proton-proton collision. So if we look from the other side of these wheels, now you can actually see there are two different wheels. So there's this wheel with these golden, orange, yellow patterned detector parts, and behind is the wheel that I showed you before, so the one with the tubes. Both of these wheels are actually part of the muon system, and the former you can see here on the left, they are part of the triggering system. So in case we see a track there, we know, okay, there was a muon, and this is already interesting. So this then says, okay, we want to keep this event. And so there's like the hardware trigger. There are also other detectors inside ATLAS there that are used for the same purpose. And this is already reducing the data to, I think, 100,000 events. And then afterwards we have a software trigger that gets us down to 1,000 events. So this is then actually what we can really save. So just to talk quickly about the detector structure. So you see the wheels here. In general, our detector is kind of built like we have end caps. So this is basically, you can think of it as a can. So we have many cans stacked into each other. And the barrel part is what we see here. So these are all the cans kind of stacked into each other. And then we have many lids on the side. So this is like the biggest lid. So if we use ATLAS, then all of this, what we see here, will be pushed inside. And then this wheel closes the whole thing. So this is what we want to show you now here on the poster. Maybe you want to show it? Yeah.
So basically this is a huge detector. So what you were seeing is just a tiny part, and it's difficult to get the full perspective of what is actually going on. So this is our beautiful ATLAS detector. It has this onion shell structure where it has different sub-detectors, as we were more or less discussing, but here you can see it a bit more clear. So this is the beam pipe, right? Like this is the beam. So basically one bunch of protons come like this, and another bunch of protons come like this, and in the very heart of the ATLAS detector they collide. And then they encounter different sub-detectors. So the first part is the tracking, that we more or less discussed a bit. This tracking is basically taking pictures. It's a pixel camera. So it takes pictures of the tracks of the particles. So some particles do like this, others do like more like that. And depending on how they curve, we can measure their properties. For example, their charge or their momentum. Because we have a very important part of this detector, which are the magnetics. The magnetic system that we can discuss, but okay. So after the inner detector, we have the calorimeters. So the inner detector, the traces, the tracks. And then we have the calorimeters, where basically they want to destroy the particle. So the particle comes happy, leaves tracks, and then encounter the calorimeter, and it destroys it. And all the energy that the particle was having is left in the calorimeter. So you have a lot of energy deposits, in cells of energy deposits. And there are two types. The green one here is the electromagnetic, and the orangey one is the hadronic. Basically, the electromagnetic is for photons and electrons, and the hadronics are for like the powerful ones, like the hadrons. Here is the Large Hadron Collider. We collide hadrons, which are composed particles by quarks. Okay, so here, for example, a proton, not a fundamental but a composed particle, can be absorbed. Then we have the here is the toroid magnets. That is very interesting because there are 8 of them. They are huge. We can see them after this. Actually, ATLAS is called a large toroidal apparatus.
LHC apparatus. I think that's where the L comes from.
The toroids are basically what gives the shape of ATLAS. And this gives a huge electromagnetic field that help us bend the particles so we can easily detect them. And then in the upper, more outside part, we have the muon chambers. Here we have these muon chambers, but we also have this wheel that we were seeing before. What is super interesting here is to see the dimensions. This is people. So this is me. Well, okay, me is half of it. So this is a person, and we are like looking this part. Well, yes, or this part. I don't know which is side A or B, but in between this. So this is what we can actually see. In this moment, this magnet here, it's a bit out. We can see it again so you can remember. This is out, and this, there are 2 muon wheels, and these 2 muon wheels are like this, goes stick to this one, and this is out. So that's why we were able to see the also newest one wheel inside, and a bit of the toroid structure. So we can go again and remember a bit of the parts.
I think what is also important is to mention that usually there's a shielding. So you see here the blue part. This is the shielding of the LHC. So we're kind of exactly at the LHC level here. So this is where the beam goes, if it's on, and then it goes through there. So right now this shielding is off, so that we have this whole building. This is the cryogenics of the end cap toroidal magnet. So this whole thing we've seen in the picture, this is being pulled out. Actually, what I mentioned before is that some of the things were transported as a whole. So this thing came through the hole as a whole. This is gigantic. Also, the other toroidal magnets, so these are actually the tubes with the orange stripes. These are the 8 toroidal magnets that we have for the barrel part. So they have a magnetic field which kind of goes around this barrel part. And yeah, it's kind of a very complicated magnetic field. It goes up to about 4 Tesla. It's actually due to its shape, it's a bit different in different parts. But yeah, so this is being pulled out. You can see inside to the muon wheel. Yeah, there's new small wheel, which is also part of the muon wheel. So basically all the toroidal magnetic fields, they make sure that the muons that go through the detector are being bent. Because this is what happens when charged particles go through a magnetic field. Their trajectories are bent based on the charge, either well, this side or the other side. We also have another magnetic field inside, so another magnet. This is actually a solenoid magnet. This is around the inner detector. And yeah, so we mentioned before that we have, you mentioned before, both then, that we have a tracking detector inside. So the innermost part of ATLAS is the inner detector. It consists of 3 different detectors. The most inside is the pixel detector, and this is really very similar to your phone. So we have a silicon chip which is pixelized, and there's a sensor material which is active. So we have a sensor coming through, and then there are electron hole pairs created. So it's kind of similar to the gadgets detector that I mentioned before, the muon tubes. We have some kind of ionization happening. And then there are electrons, so electrons create an electrical signal. Basically what we do is we transport this signal out through the cables and fibers, everything, to get a signal. So this is what happens like in the pixel detectors, really like your phone camera, just many, many, many more. Around that we have a strip detector. So strip is just an elongated pixel in a way, kind of the same thing and bigger. And around that we have now also gaseous detectors, a transition radiation detector. And yes, so what I find very interesting about this is that the whole thing will be replaced. Okay, so a bit of spoiler alert, I'm working on the replacement of this detector, so I find it obviously super interesting. But it's a cool thing, because so I mentioned that this gigantic thing came down as a whole, and what will happen is that the whole inner detector will be moved out, taken out through the access shaft, and then a whole new inner tracker will actually be moved in. It's called the ITK, so just the inner tracker of ATLAS, and it will be a bit different. So it won't have the inner silicon layers, silicon sensors, and outside gas, but it will be completely made of silicon sensors. So this is a very cool thing.
Yeah.
And yes?
So now that we have a bit of questions, that's awesome. Thank you for the questions. So we have one for Raul. Now that you are talking about the magnets and everything, how does it control the direction of the particle when it's traveling near the speed of light? So.
Well, okay. So I mean, if we have a magnetic field, then this magnetic field has an it has it acts on moving particles. So if a charged particle is moving, that's based on the equation, there is a velocity in there, so it will bend the track. But now the thing is, if the particle is very fast, the track won't be bent very much. So basically what we need is a very strong magnetic field so that even very fast charged particles can be bent. This is also one of the reasons why the detector is so big, because as I mentioned, the muons are 200 times heavier than the electrons. So while the electrons are being stopped in the calorimeter, the muons actually travel through. And we do still want to see somewhat of the bend, because otherwise it's meaningless, the information we get. So it needs to be very long and very strong magnetic field so that it is actually a tiny bit bent. In order to achieve that, we do actually use superconducting magnets, which I think is very interesting. So we cool them down to something like 4 Kelvin, so that we actually reach superconducting, what is it called? Superconducting state.
Yeah.
And yes, so this is how we actually manage to bend our particle trajectories.
Yeah, which is related to another question. They say, so is those magnets that gives those particles its initial speed when it starts the initial journey at velocity? And actually, yes. Like all these superconducting magnets that we have are not only giving kicks, but also are trying to bend the trajectory. And it's not just the LHC. We were talking before that there are previous accelerators, complex, SPS, that tries to first they start with this bottle of hydrogen. You take the protons and then you start with a smaller accelerator. Then they are injected to a bigger accelerator, and then to bigger. And then they start to gain more energy, more acceleration, and then they are injected to LHC to acquire almost the speed of light. So, and all of these is done with supermagnetic magnets that actually we can have a look at it, no? We have more or less, well, not at it directly, but the dipole here. No, it's not in this floor.
I think it's one down.
We can go.
Yeah, so what is important to mention is that the acceleration we actually do with an electromagnetic field, and then the bending of the particles is done with the electric field, and the bending of particles is done with the magnetic field. So if we didn't have these superconducting magnets, our particles would just go straight, which is not helpful because we want to save our particles, right? We have these bunches, so we want to keep them in the LHC for quite a while. That's why we need to bend them. So that's why we have these super strong magnets, and then they go around. So while we go to where you wanted to show us something, let me just quickly explain about the few cycles of the LHC. So we can basically say we have 3 different cycles. We have, when we have steam inside the LHC, it will be there for about 20 hours, and then it's kind of used up. So this means that so many protons have already collided that at some point we actually need to dump the beam and then refill the LHC. So like on a daily basis, we have kind of beam, and then it's being dumped at some point. Then there is a second cycle. This is like the yearly cycle. So we usually from say like March to December or November, something, the LHC is on and running and giving us data. And then we have a small maintenance break. So in the winter time, we can do maintenance work or small repairs, small exchanges, cables, whatsoever. And then we have the like big cycles. So this is the shutdown or run times. So we have every few years, we have a long shutdown where we can actually do a whole detector replacement, like what we mentioned before. The new small wheel came down, and the next thing I also mentioned is the ITK being inserted. That will happen in the next long shutdown. And right now we're in a run period, so yeah, we have these like daily cycles, yearly cycles. And why we're even here is because we're now in a shutdown period, because otherwise we couldn't be down here. There would be beam and it's impossible.
Yeah,
But, yeah.
And also super nice to tell the people that the shutdowns are in the winter period.
Yeah.
Because the amount of energy this LHC needs to take to work, it's huge and is on the same order of the energy that Geneva needs to heat their houses. So in winter we shut down because it takes so much energy. But then, okay, don't worry, in March we will start again our operations. And now we can show them, no? Maybe I could go down. That's what I have.
I mean, you're short, but you're not that short.
So yes, actually, I can manage.
Brava.
So this is, yay. So this is what we were talking about. This is LHC beam pipe is passing like here, and this is a shield in because okay, there is a lot of radiation, so we need to protect it. And then there is the dipole, which is this magnet.
Magnet.
What?
Magnet.
Yeah, superconducting magnet. This is what I wanted to say.
Okay.
that help us to accelerate and bend the particles at the LHC, and then they come in this direction, this bunch of protons, and then collide inside that direction. So yeah, this is super nice to see, right? Okay, let's crawl out of here.
So what I think now we should do is go
That's why we need a helmet.
That's why we need helmets.
we can go like 1 or 2 floors down, and then you can actually walk down to the detector a bit. From here. Now we go around the detector. Okay, so now we get a bit of a different perspective. You see again the same things we talked about. Part of the big neon wheel, the end-cap toroidal magnet. Inside you see this new small wheel. Then we see again these toroidal magnets here. And all along this direction now is actually, ATLAS stretches in this direction. So what I want to mention while we're here are just 2 things. So we didn't say that ATLAS is actually very heavy. So ATLAS is about 7,000 tons heavy, and this is about as much as the Eiffel Tower. Also, you see here the cavern, right? There was stone, whatever, inside. So now the fact is that ATLAS is actually not as heavy as the thing that was excavated. So what happens is that the cavern floor is kind of going up. It's going up by, I think, 0.5 millimeters per year or so. So what we need to make sure is that we understand where exactly we are. So where exactly is the detector? Everything needs to be aligned. So due to that, we have these geodesic points, like for example this one, where they do actually measurements all the time to really understand where exactly is ATLAS with respect to the cavern. Also, we mentioned before the 4 experiments at CERN, at the LHC, sorry, there are many, many more experiments at CERN. We mentioned all the other accelerators, there are lots of different experiments. We're just down here at ATLAS and slightly in love with it, so we'll talk mostly about it. But the sister experiment of ATLAS is CMS. It's a compact muon solenoid. Why is that important? Because, well, if we would throw ATLAS in water, it would swim. However, CMS sadly sinks because it's much, much, much heavier. Well, but why are these 2 so important? Why am I talking about these 2? Because both are general purpose detectors. So when we were talking about the physics we want to do, like understanding the particles and the origin of matter, we have these 2 general purpose experiments that kind of want to do the same thing. So they both have a tracking detector, calorimeter, and the muon system, but they build in completely different ways and independent from each other. Because the idea is that the physics that we find, they should kind of be cross-checked by another experiment. So we have these 2 doing the cross-check. Yeah, maybe you can talk a bit more about the analysis of what you do.
No, well, I was going to compliment on this because I think this is a beautiful concept of science in the scientific method. The possibility, the falsibility. Like that one experiment, say, okay, I discovered the Higgs boson. If there is another experiment that cannot corroborate, there is no discovery. And this is very beautiful of the science. One can say like, yes, I discovered dark matter, but if other experiment in similar conditions does not see dark matter, there is no dark matter. Or yes. So that's why we have ATLAS, and we have at the other side of the ring, the CMS. And we are basically this general purpose doing more or less the same physics because we want to compete, but in a scientific sense, to get the results and to corroborate and to cross-check our results, which is very nice. Then this is also super cool. This is the beam pipe because we saw the dipole. You see, like this one is super small. Of course, okay, it's carrying protons. It should not be huge, but there you had the dipole with the shielding. So one can think it's big, but no, it's really a small little pipe where all the protons are injected, and it's super cool. We have a question actually related to physics analysis. So, Diana Carolina says, in the short term, 2 or 3 years, what will be the greatest contribution that can be achieved with the detector at its current capacity? Wow.
Okay.
So what I think is, okay, we haven't discussed the Higgs boson, for example.
Yeah, I think we're
A
throwing
little
around quite
bit.
a lot of words, so maybe we should just have like a general overview. So what we do particle physics, what we we mean is basically that we describe a theory with something called a standard model of particle physics, and what it does, it describes the particles and it describes their interaction with each other. So now what we're trying to do in these proton collisions and the events that we record, we want to understand the properties of these particles. So that's basically when we say we do an analysis of these events, that's more or less what we do. So we try to identify the particles, find out their mass, find out how strong they interact with other particles, all these kind of things. And people with you know a bit more detail about this.
Well, yeah, because in 2012 we discovered the Higgs boson, right? Which is the very first kind of boson that is scalar, which is important for the theory, but okay. That gives masses to the fundamental particles. This is a very important fundamental piece for our theory model, which is called the standard model. And it was super important 10 years ago. But now, regarding this question, 2-3 years from now, with the current data, what are we really want to know if this is actually the standard model Higgs boson? If it's actually the Higgs that the theory describes and that we discovered 10 years ago, if it's what we expect. We know the mass because we discovered it at a certain mass, but then there are a lot of properties that this Higgs boson has, or there could be other Higgs bosons, for example. So we want to really understand this part of the standard model that is quite new, more or less. We have a theory that describes it, but experimentally there are a lot of things that remind me to know the properties, if it's just one Higgs boson, if it's the only one in charge of giving the masses of the fundamental particles, or there are others that could do that. This is something very key in the next 2-3 years, exploring the Higgs sector. But something very important also, we can talk about the big fat questions of the standard model. One of it is the dark matter. And this is one of the very important key points for the future operations of the LHC, of our detectors, because we know that dark matter exists. It's super important because 85% of the matter of the universe is done by dark matter. And it's super crazy because all of these big things is just for recording 15%. And we know 15%, and not completely know, but okay. We can reconstruct, we know a little bit, okay? But for the dark matter, we don't have any clue of its quantum properties. It's like the fundamental quantum nature of the dark matter. We know that it's up there, making the galaxy rotate, making the universe do its dynamic, but here in the quantum subatomic level, we don't know. And this is something very important and present currently in our physics. In particle physics, physics, astronomy, cosmology, everybody is crazy about dark matter. So the next 2-3 years, it will be awesome if we keep the dark matter searches and if we try to find one. Maybe, who knows?
Yes. Sounds good. All right, so let me show you a bit more of the detector. I think it's very nice to see how big it actually is. So just walk past all of these detector parts.
It's a bit loud.
This is the part of the barrel that you can see from the outside, and you should have a look there. So this actually, every institute tries to put their name so that we always see who has actually built the whole thing. So you see here, this is for example in München, and it's kind of funny because now everybody thinks they built the whole detector. Of course they didn't, but we have gigantic collaborations. We have many institutes taking part, and in total there are about 3,000 scientists that are working on ATLAS. So this means that in the papers we write, there are also 3,000 authors. Isn't that fantastic? So now we are at the other side of ATLAS. It might be actually a bit louder here, but what I wanted to show and see that you can have a look is that they should be symmetric. So you do see the same wheels, you see the same AMP-cap toroidal magnet, and we actually see the new small wheel being out a bit. So this is quite nice because we can actually look inside and see through. We do see the end cap of the hadronic colorimeter. Okay, I know it's there. I don't really see it so much. There's a bit of aluminium that we can see. So this is kind of very cool. Also, we see how this whole thing is moved. So you see this kind of the arm that comes out from the crane or from below the crane. So this is how we move our thing. And also you see this orange structure here on which we actually position everything that we take out. So obviously in run configuration it's not there because then everything is pushed together and we can actually run. Let's go back.
Yeah, we have okay, because the sound is
exactly. Here it's more advanced, so we're just going to go back. meters underground, so it's kind of a long way it needs to travel to our computers.
Yeah.
All right, are there any more questions?
Yes, the people are super curious to
We go
know.
downstairs.
Because of the sound.
Yeah.
Okay, let's go. But don't forget to put more questions.
Yeah, so if you have more questions, I think we can also soonish come to an end. So if you have some more urgent questions, please let us know. And we will get to you like in
We go down on this one? Or is that the other one?
It would go the other one. We can just go all the way down so that we get in like a full view about this kind of full view. All right. So what I think is also kind of interesting is that really the way when Atlas was built, everything was like handmade, put together, and then so we need to know exactly where which part of Atlas is, right? So we use particles, sure, from the collisions, but in order to align, we actually use cosmic particles. So muons are coming from the universe, they come coming through here, and then basically what we expect, if no magnet is on, it should go straight through. So we expect a line going straight through all the detector elements. What I heard is now when they built the whole thing, they saw a track that was kind of like this. So obviously something was switched, the cable was put in the wrong position. So now we of course have to do some software alignment so that we actually get a straight track and not some kind of zigzag track. I think it's kind of really cool. So we always need to make sure that we can correct for these human mistakes. All right, let's go all the way down. Yes, so we have the whole view of Atlas. So you can see how big it actually is all the way to the axis shaft. On the other side we have the same thing, so also an axis shaft, they take different size, but it doesn't really matter. What you can also see here on the left is maybe instructed, I don't know what it is, but it's a tank of either liquid argon, which we use for the calorimeters, or maybe liquid helium, or anything. So we have quite a lot of gases that we use in our detectors, but also for the cooling of the superconducting magnets we need helium and liquid nitrogen. So yes, like you see, the infrastructure is gigantic in this cavern. All right, are there any further questions?
Yeah, the people were curious about the collision point.
The collision point?
Yes, if the temperature will change, if something happens, what happens in the collision point?
Well, in the collision point, the collision is happening.
But like, if there is sound, the temperature change?
No. I wouldn't say so. Also, the collision point, maybe we didn't point it out yet, it's in the middle there. So right in the middle of Atlas is where they actually collide.
Yeah.
And
Yeah, also because in order to have sound, you need waves. And for having waves, you need to have air. And for having air, you need particles. And this is supposed to be super, ultra, mega hermetic. So,
down there, so
yeah, we have it super vacuum, so don't worry, it will not sound. Or it will not change.
Are there other questions?
Well, I don't see more.
Okay.
And I don't know, maybe I am not having, or maybe Katarina knows.
Yeah, there's what about electromagnetic radiation if it is nearby? So
Yes, so this is actually a good point. There was a question about electromagnetic radiation. So what we need to do is on our detector to shield it, of course. That's also one of the reasons why it's underground. Because we have all this stone, or just, ground above us that will shield us from other particles, so from electrons or photons, which is electromagnetic radiation, the photons in principle. So basically we shield it through that, but then also around our electronics and everything, we do also put shields. So they're built like everything, not everything, the things that are shielded are inside Faraday cages so that there is actually no other electromagnetic radiation coming in. That's a very important point. So we really need to make sure that our detector is properly shielded.
then there was one about the known property. What are the known properties of the Higgs as we understand them presently?
Yeah. Well, but something before that we forgot to say is that we are 100 meters.
Yeah, we said it.
Yeah, okay.
Well, 100 meters underground, yes, exactly.
Okay. So about the properties of the Higgs. So the Higgs is very interesting because, well, the thing that happens is that in the beginning of the universe, all the particles were massless and they were free and it was a lot of energy, and it was so weird because we know that the carriers of the electroweak force, like the electroweak force that is related to the electromagnetism, to the, okay, have to be massive. So what happens with the Higgs is that it breaks asymmetry. So now with the Higgs, it doesn't exist alone, but what it does is that it interacts with these particles, breaking the symmetry of the particles not massive, and then give mass to the particles. It's a complicated theory, which is very beautiful. It's done by Emmy Noether. I don't know how to pronounce it actually. How is this?
Noether.
Wow, the German. That talks about the symmetries and all these mathematical Lie groups and okay. So it's very special because you cannot find it alone. For example, when we discovered the Higgs boson, you don't say, okay, this is a Higgs boson. We find it because we reconstruct it from its decay products. So usually the Higgs likes to decay to quarks. So we take quarks and we recreate, like doing a bit of criminal forensic science, and we say, okay, this could be a Higgs candidate. And we do this a lot of times, so that is statistically significant, and we can say, okay, we'll find a Higgs. So it's very special because how it couples, how it interacts with other particles, because it gives, with its interaction to the fundamental particles, their masses. And yeah, I think that's super cool. It's the only particle that does this.
Yes, and I think this was actually very nice what you said, that it's kind of like criminals. So actually what we're kind of the detectives. So we do have the collisions and we don't know what actually happened. We just see what came out. And then what we're trying to do is reconstruct from that was there, what was there before.
Yeah.
So we look at the signals in the detector and then we try to find the Higgs. Yeah, I think maybe we can conclude with this.
Yeah.
And
Okay.
yes, thank you very much for tuning in. We hope to see you again, and if you have further questions, you can also come and visit CERN. So we have lots of offers for students as well. You can come with your school classes, there are labs. We have a gigantic visitor center. We have also in-person visits. So yes, we hope to see you again.
Super important also. There are virtual visits. So you can go into the webpage, maybe we can put the link later, and you can request a virtual visit in the shutdowns. And we can do this with your classroom, with people you know in your master class. Okay, I don't know. But you can request it, so we can do this with your people. Yeah.
Great. All
Okay,
right.
it was awesome to have you here.
Bye-bye.
Ciao.